Alright, so our new vocab word for today, we're going to discuss what's called a point of inflection. Am I correct in assuming like we've never heard that before? Probably not. Okay. So point of inflection, we'll get to the definition in a second, but I kind of want you to understand where this vocab term is coming from. If you take a look, for instance, at this graph at the top of the page of 149, if you were to trace it from left to right, do you realize when you trace it, it initially...
Good morning.
Good morning. Anything for the office? Go ahead. Bye, have a good day. Alright, so if you were to trace this graph at the top of the page, when you initially start to trace it, do you realize how it kind of has an upside down parabola type look to it? But if you were to continue to trace it, doesn't it kind of change to a regular parabola look? Okay, regular meaning going upwards. And then if you were to continue to trace it, wouldn't it then kind of look like an upside down parabola again? Okay, so when we have these polynomials, these roller coaster type graphs with all these humps and bumps, they have certain curvature to them. Some intervals or sections look like upside down parabolas. Some sections look like regular parabolas or U-shapes. So we're going to start to identify here where this curvature is described. Where does it look like an upside down parabola? Where does it look like a regular parabola? And we're going to define a point of inflection as the particular spot where the curvature changes. Where does it go from kind of pointing down to kind of pointing up? So for instance, in this picture here, wherever my red line meets the blue line, because that's where the curvature would change, you'd go from an upside down parabola to a right side up parabola. This is what's defined as a point of inflection. Okay, that special point on the graph where the curvature changes. So we're going to go ahead and write that down in this box. We'll say the point on the graph where the curvature changes. But from this point forward, you're not really going to hear me use the word curvature. There's kind of another vocabulary term that we're going to talk about. Have you heard of the word concave before? Maybe in a science class when you talk about lenses, like concave and convex. The specific curvature of a graph is referred to as its concavity. So in that little parentheses, that's what I want to put in there. The concavity changes, basically meaning curvature. Alright, so what we're going to do in the little box below that, okay, it's basically the same graph as above, we're going to go ahead and identify how many points of inflection does this graph have. So if you were to start to trace it, notice how it's initially kind of an upside down parabola, and at some point it's going to change to a regular parabola type shape, like a regular looking U, and then at some point again it's going to change, and notice how it kind of looks like an upside down parabola. So how many points of inflection does that have? How many points do you change from a regular parabola to an upside down parabola? Can we label them? How many places how many places does this graph change from red to blue or blue to red? Yeah, we got 2. Yeah, and we can specifically label them. Okay, so we have 2 points of inflection. Okay, we have two spots where the curvature or concavity changes. All right, we're going to be a little bit more specific with this too. My little red sections here are where the graph looks like an upside down parabola. That's commonly referred to as concave down. Okay, the curvature of the graph is kind of pointing downward. So we'll label those as concave down sections. But my blue section, if it looks like a regular U-shaped parabola, that's referred to as a concave up section, because both ends look like they're pointing kind of upwards. So we're eventually going to get to the point where we're going to identify concave down intervals, concave up intervals. We're describing the curvature of the graph, aka concavity. Okay, now if we can identify how many points of inflection we have, maybe we can also identify specifically the point values themselves, like the ordered pairs. So we're going to discuss kind of where these points of inflection happen. And then we actually have three things or three places where a point of inflection can occur, okay, where the concavity changes. One of them I think is actually pretty apparent based off of this graph that we just did here. From yesterday we talked about maxes and mins. So notice how we have a maximum at this high spot and a minimum at this low spot. Can you kind of describe where this point of inflection is in relation to the max and the min? Yeah. It's in the middle, right? Okay, so one of the places where a point of inflection can happen is in the middle of a max or a min on your graph. Okay, that's kind of the more easier one to spot. The other two are a little bit harder to initially think of, but I think after we draw a picture, at least talk about it, they'll start to make sense. I don't want you to draw this, okay? I just want you to visualize what's going on here where another spot is. What if we had a graph that had a multiplicity of 3? Okay, somewhere at that x-intercept. Multiplicity of 3, we go through the x-axis, but we're level, right? If you were to trace this graph, notice how the first section kind of looks like an upside down parabola in its curvature because it's kind of pointing downward. Whereas if you were to continue, the rest of it looks like it's concave up, like a regular parabola, because it's pointing upward. So notice how if you go from one section of concave down to a different section of concave up, you must have a point of inflection in there because you're changing the concavity. So another place where a point of inflection can occur is at an x-intercept with a multiplicity of 3. Can we visually see that? Like if we're level at the x-axis, the first section is pointing down in this case, and the second one's pointing up. So you have that curvature change, meaning there's a point of inflection. Can we see that? Okay, so I think the first one's pretty apparent to us. The second one hopefully is now, after we kind of talked about it. The third one is kind of the difficult one of the three. We're going to figure out, and we'll see some examples of this one as we go through the rest of the section. We're going to figure out the middle of an x-intercept with a multiplicity of 3 and a max or min. I'm not going to draw an example of that, at least on this page, because we'll get to one of those in a little bit. Okay, so we have 3 places where the concavity can change, aka point of inflection. in the middle of a max or a min at a multiplicity of 3, or in the middle of a multiplicity of 3 and a max or a min. Notice how the third one kind of brings number 1 and number 2 together, because it deals with both of those concepts. Okay, so what we're going to try to do is, based off these other two graphs at the bottom, we're going to try to label but also identify the coordinates, like the actual ordered pairs of all of these points of inflection where the concavity changes. So what I want you to first do is maybe trace it with your pencil, okay, and try to locate where the point of inflection might be. Let's see, if you start to trace it, it initially looks like an upside down parabola. Okay, that's concave down. But at some point it's going to change and then resemble concave up, like a regular parabola. So wherever you think that change is, that's where your point of inflection is. Alright, so what we're going to try to do is, we think it's roughly there, but we're going to figure out exactly where it is. Okay, what exactly is that ordered pair? So this point, if we labeled it as a point of inflection, is happening at one of these 3 instances. Is this point of inflection in the middle of a max or a min? Is this point of inflection an x-intercept with a multiplicity of 3? Or is this point of inflection in the middle of an x-intercept with a multiplicity of 3 and a max or a min? Can we identify which of the 3 this one is? What do you think? It's the middle of a max or a min. Here's a max, here's a min, and our point of inflection looks roughly in the middle of it. So we're going to try to figure out the exact middle of that max or min. Can we label what the max is in terms of its ordered pair and what the min is? We did that yesterday. We should be able to do it today. Let's see, the max looks like 1,4 and the min looks like 3,0. Does that sound about right? Okay, so if this point of inflection is happening exactly in the middle, we're going to analyze these x values and y values to try to figure out what's in the middle of those. So let's go ahead and label the point of inflection. Sometimes I refer to this as a POI, instead of actually writing out point of inflection, because that's kind of long. If you want to abbreviate it, okay, point of inflection, that's okay too. Alright, so let's take a look at the x values first. What's in the middle of 1 and 3? The exact middle. I think we can figure out that's 2. Okay. What's in the exact middle of 4 and 0? Or 0 and 4 if you want to put them in order. Yeah. 2 also. Okay, so according to this relationship of concavity and point of inflection, this point we identified should be 2, 2. And doesn't it look like we labeled it as that pretty close, right? Just off of our estimation of where it might be. Alright, so one of the things that we're going to look for, at least in terms of these 3 places, is the middle of a max or a min. Okay, where that concavity changes. Let's go ahead and check out the next one. Okay, so if you started to trace it, the initial curvature looks like concave up. If you were to continue to trace it, looks like concave down. But at some point it looks like it's going to change to concave up again. Okay, like a regular parabola. So how many points of inflection do we have to find in this case? We got 2. We got 2 places where my red and blue changed. Okay, so we'll guess as to where those are right now. But we should be able to figure them out exactly, okay, because if these are points of inflection, they're happening at one of these three places. So let's see if we can figure out the first one. So this first one, is that in the middle of a max or a min? Is this one an x-intercept with a multiplicity of 3? Or is this one the middle of an x-intercept with a multiplicity of 3 and a max or a min? Can we think about which of the three this one is? Yeah. Say it again.
Number 3.
This one?
Yeah.
So if this is in the middle of an x-intercept with a multiplicity of 3 and a max or min, where's the x-intercept on either side and where's the max or min on either side? If this point is in the middle.
Oh, okay.
It's 2. Okay, this is an x-intercept, right? It's on the x-axis. Number 3 is a point in the middle of an x-intercept. Okay, not an x-intercept exactly. So number 2 is the only one. If you have a point on the x-intercept, it's or on the x-axis, it's mostly or probably going to be this one, an x-intercept with a multiplicity of 3. So what we just have to do is identify what that x-intercept is, and that's our point of inflection. We don't really have any calculation to do like we did in the last one. It's just simply the point or x-intercept itself. So we'll label this first point of inflection, or poi, as -2, 0. Right, so that's that one. But we had another one that we labeled, so let's try to figure that one out. This other point of inflection, is this in the middle of a max or a min? Is this an x-intercept with a multiplicity of 3? Or is this point in the middle of an x-intercept with a multiplicity of 3 and a max or a min? What do you think, Ashlyn? Okay, so here's a minimum. Where's your maximum on the other side? We do have a min. What do you think, Tori? Right, this is an x-intercept with a multiplicity of 3. So this point of inflection is actually an example of the third one. Notice how this point is in the middle of an x-intercept with a multiplicity of 3 and a min or max. In this particular case, it's a minimum. Okay, a little tricky there. So we're going to have to figure out another middle point, kind of like how we did in the last example. So if we were to label, well, we already labeled the x-intercept with a multiplicity of 3. That was -2, 0. Let's go ahead and think about the minimum, which Ashlyn identified for us. Looks like 1, -5. Okay, so this point of inflection, if it's in the middle of those, let's go ahead and think about the middle. So what's in the middle of -2 and 1? It's a little tricky. Yeah? Not quite. Because if you think about a number line, -2's over here, 1's over here. This is 1 unit away where this is 2 units away. That's not exactly in the middle. What's in the middle between 1 and -2? Yeah? -1/2. Okay, so this is 1.5 units and this is 1.5 units. So that's going to be in the middle. So we have a -1.5 x value. A little tricky because it's a fraction. Let's do the same thing for the y's. Okay, what's in the middle of 0 and -5? So maybe we'll change our number line. It's in the middle of 0 and -5. Yeah? -2.5. Okay, so we'll go ahead and write that down. You can write it as a decimal, as a fraction, either one's fine. Alright, so if we were to check this roughly, because remember we estimated this before, this black dot right there kind of looks like it's at -1.5, comma -2.5. We're a little off because we were guessing, but I'd say we're pretty close. Alright, so points of inflection, they can happen at 3 places. Our first example was in the middle of a max or a min, so you got to figure out what those middle values were. The second point of inflection was that multiplicity of 3 on the x-axis. And our third example was in the middle, kind of the trickier one, the middle of that x-intercept and a max or a min. So there you have an example of all 3 cases. Okay? What we're going to do now is continue with this idea of points of inflection, but we're going to use the points of inflection to help us determine the intervals of concavity. Okay, where are we concave up? Where are we concave down? Because those points of inflection are the changing spots. So those are kind of our beginning and ending values that we're going to use to help us with these intervals. Okay, so in formal definition, we'll say these are intervals along the x-axis where the graph is concave up or concave down. Now, to make this a little quicker or easier for us at least to identify, these are the same 2 graphs that we just did on the other example for the points of inflection. So we're going to go ahead and label those points of inflection like we did before. Okay, so this first point of inflection we had, we said was 2, 2. In the other example, we had -2, 0 and -0.5, -2.5. All right. So if you were to trace your graph, we'll do this first one here. If you were to trace your graph from left to right, and you were then to stop at that point of inflection, would this first section be concave up or concave down? Does it look like a regular parabola that goes up or an upside down parabola that goes down? Can you describe the curvature? Concave down. Okay, so let's go ahead and label that interval. Okay, so think about your interval if you were to drag your pencil. Looks like, since we have an arrow on the end, this would go forever to the left, towards -infinity. And as we drag our pencil across, we're going to stop at that point of inflection because that's where we are no longer concave down. It looks like that point of inflection happens at an x value of 2. So we'll end our interval there. Okay, we're going to use a parenthesis. Even though I know there's a closed point there, this location of 2 is where your concavity changes. Okay, you're not concave down at that spot. You are changing from concave down to concave up. Kind of like the increasing and decreasing. They're always going to be parentheses because you're changing the curvature at those points. Alright, if we were to continue to trace, this time we'll be on the other side of the point of inflection. And if we continue, we're eventually going to reach an arrow. Notice how that section looks like a regular parabola, so we'll describe that as concave up. And in terms of dragging your pencil, looks like the blue section starts at 2 and is going to go off towards infinity. Do you guys think you can try the next one? If you were to trace your graph, what would the first section look like to that point of inflection? What would the second section look like? What would the third section look like? Any takers? Where's that graph concave up? Where is it concave down? Can we identify any of those sections? What do you think, Ashlyn? Go ahead. Okay. Alright, so she's referring to this first section here. Okay, notice how based on the curvature, if you were to continue kind of the parabola shape, it would continue to go up on the other side. So it looks like that would be concave up. You want to keep going? There you go. All right, so for the second section that looks like a regular parabola, it starts at that -1/2 point of inflection we identified, and it's going to continue forever to the right because we have that arrow. Looks good. That's not an 8, that should be an infinity. All right, so we do have this other middle section. Notice how it kind of looks like upside down, because if you were to continue the other side, it would be that upside down parabola shape. Okay, so that would be our concave down section. Looks like we go from point of inflection to point of inflection, which would be interval-wise -2 to -1/2. How'd you do? Pretty good? Alright, so far so good. So what we're going to try to do, okay, step it up a bit, is kind of bring everything together. All these graphical characteristics and concepts that we've been talking about this year, we're going to identify basically all of them off of one graph. We have domain, range, intervals of above x-axis, below x-axis, end behavior, maxes, mins, points of inflection, concavity, x-intercepts and multiplicities, all this good stuff. So what I want you to try, because I think we're good at these up to this point, I want you to try domain and range, 0 multiplicities, f of x is bigger than 0, f of x is less than 0, type of function, and increasing, decreasing, and maybe go ahead and try maxes and mins from yesterday. Okay, can you guys try those real quick? We'll save the other ones because I want to talk about those. Those are a little bit new or different for us. Alright, let's tackle domain and range first. Drag your pencil left to right, low to high. What'd you get? Domain, range, either one? Yeah. All real numbers for both, that's good. Or you can use negative infinity, positive infinity interval, that's okay too. I agree, so far so good. What about zeros and their multiplicities? So where are the x-intercepts and what type are they? Could you identify those? Good, Dylan?
Zeros are -2, 1, and 3.
Okay.
Multiplicity of 1.
All multiplicity of 1. How'd you know? That's good. How'd you know though?
They all strike through the x-axis.
They all strike through. Right, go straight through the x-axis. Looks good. Alright. What about where f of x, meaning the graph, is greater than 0? AKA your y values are greater than 0. Any takers? Yeah? Okay. Okay, and what were you looking for to get those intervals? Those are great. Above the x-axis. Good. Okay, so that checks out. What about if f of x is less than 0? So kind of the reverse idea. Where's the graph below the x-axis? What did you label for those sections? Good, Dylan?
Negative infinity and -2.
Okay. 1 to 3. So far, so good. How we doing? All right, let's keep going. We'll talk about left and right end behavior in a second. What about the type of function? So can you give me the name of this graph? Yeah. Y. Good. Okay, so it has the two maxes or mins. Okay, those two humps or bumps. That's one way you can think about it. A little bit more accurate or specific is the multiplicities. If you add them all up, they add to 3 in this case. Notice how you have 3 x-intercepts, all multiplicity of 1. 1 plus 1 plus 1 is 3. Okay, so you could use the hump or bump idea. You can use the multiplicities. Either one is a pretty good justification. Cubic because we'll say, or at least I'll write on here, the multiplicities add to 3. I don't have a lot of room in that box to write everything you could look for. What about where your graph is increasing? If you were to trace it left to right, where would your pencil be going up? Good, Brianna?
2 to
3 to infinity, perfect. What about decreasing? Pencil going down. Good, Dylan?
-1 to 2.
-1 to 2, so far so good. What about, oh, we froze. There we go. What about relative maximums? Okay, so vocab term from yesterday. Relative max. Can you identify a point on the graph? Go ahead, Hannah. -1,5. All right, so there's a maximum. Looks good. What about a relative min? Is there a low point on your graph? Go, Dylan.
2,
-2,
-2.
-2. All right. What about the other types of maxes and mins? The absolutes. Absolute max, absolute min. Do we have any of those? Yeah. All right. So absolute, we're looking for the highest or the lowest point. Notice how what we've identified for the other two cases are general high points and low points, not necessarily the highest or the lowest. But since we have arrows pointing up and down, that means we're never ever going to reach the highest spot or lowest spot because the graph's going to continue forever. So we don't really have either of those in this case. How'd you do on your own? Pretty good. I see head nods, which is good. All right, let's talk about what we didn't identify yet. So the first one is the left and right kind of end behavior. Thank you. I saw some pencils moving, I think, along this one. Left and right end behavior, if you were to just trace your graph to the left, we want to describe what it's doing. And if we were to just trace the graph to the right, we want to describe what that one's doing. So as the x's get smaller, meaning towards the left-hand side, what are the y values doing? How is your graph behaving? What's the left side of your graph look like? Yeah. It's heading towards negative infinity. It's going down forever. Okay, very similar idea for right end behavior though. As x approaches positive infinity, okay, as we travel to the right on a number line or the y-axis, the y values look like they're going up forever. So we'll say positive infinity. We're going to deal a lot more with that in the next section tomorrow. Alright, so we saved kind of the best ones for last at the bottom. Okay, the new concepts for us, this concavity and points of inflection. If you were to trace this graph, okay, from left to right, let's go ahead and kind of analyze the curvature. So if you initially trace it, looks like we have an upside down parabola, but at some point it kind of changes to a regular parabola, concave up. So we do have some point of inflection, some place where it changes. Okay, that curvature goes from concave down to concave up. So let's see if we can identify where that point is specifically. So based off of this graph, okay, that point of inflection, it's either in one of three places. Is it between a max or a min? Is that point an x-intercept with a multiplicity of 3? Or is this point in the middle of an x-intercept with a multiplicity of 3 and a max or a min? Can we determine the type so that we can figure it out? Yeah. It's in the middle of a max or a min. All right, and we already know what the max or min are because, well, they're listed for us on the graph, but we also identified them in our little table. So we said the max was -1,5. The min was 2, -2. Let's go ahead and figure out the point of inflection. Okay, what's in the middle of those? So look at the x values first. Maybe think of a number line to help you out if you have to. What's in the middle of -1 and 2? Yeah, it'd be a half. So far, so good. All right, and then let's take a look at the y values. What's in the middle of 5 and -2? Or -2 and 5, if you want to go in order. Think about a number line. Maybe this will be a little shortcut for us. What's the distance between -2 and 5? How many units or tick marks would you have? Yeah. 7. So then what's half of 7? What's in the middle of 7? 3.5. Okay. So we need to go either 3.5 units this way from 5 or 3.5 units to the right of -2. So where would that lead us? Yeah. 1.5. Okay, maybe that might be a little process to help you guys out. So we'll do 1.5 there. Okay, so now that we know what this coordinate is exactly, okay, even though it's not really listed, we'd have no idea what the tick marks are on the y-axis. We know exactly where this one is. We can use that point of inflection to help us list the intervals. Where are we concave up? Where are we concave down? So our first curvature we drew is concave down. It looks like an upside down parabola. So that interval looks like would be -infinity to that point of inflection we identified, which had an x value of 1/2. And then the concave up section that looks like a regular parabola would start at that point of inflection of 1/2 and then continue all the way to the right towards positive infinity. Don't lose that for tomorrow. We're going to try another one, okay?